This is video 14.4 for our kinetics chapter, and we're going to take a look at the change of rate with time. So far, what we have looked at is we've looked at average rates of reactions between time intervals. So we began the chapter with that, looking at graphs and being able to calculate an average rate. We have also looked at instantaneous rate of a reaction by taking the slope of our tangent line on the graph. We did a couple examples of this. It's not one of the major things for this chapter, but we have looked at it. And we've also taken a look at reaction rates, writing rate laws, and showing how concentration changes can affect the rate. So those were our rate laws. Now we are going to take a little bit further look at reaction rates. We're going to take a look at how to determine the reaction order by graphing data in 3 different ways. It has to do with the orders of our reactions and how we analyze those graphs. And then we're also going to take a look at how to determine the rate constant and the reaction order from these graphs for a reaction. So we're going to take a look at the zero order reactions to get us started. We've taken a look at the rate laws for this, but haven't looked at their integrated rate law. What's nice about this one is the integrated rate law for it is very simple. In our other ones we've looked at, we had natural log functions and 1 over our concentrations, those kind of things, but this one's very simple. So it takes the concentration of chemical A at a specific time, times t, and it's equal to negative kT plus the concentration of A at time 0. So these are the same 4 variables that we've looked at in the other integrated rate laws. Nothing new at this point. When we take that equation, though, it is in the form of y equals mx plus b that we're used to in math, and it makes it very easy to graph this as a line. We'll notice that our y-intercept would be the concentration of A at a specific time. Our slope is going to be negative k, our y-intercept is A at time 0. I'm confusing myself. It's concentration of A at time 0, and our slope is negative k, negative of our rate constant. So because we can find the slope of that, it's a nice line, we can find our rate constant from the graph. Oh, well, convenient. So when this equation is graphed, we get, like I said, y equals mx plus b. We will get a straight line, which is really nice. Our slope is negative k. So if we were to find the slope of that line when it's graphed, and we would get a value, that value would be negative, and we want to change it to a positive value to get our k value. So our rate constant k is always going to be a positive value for this. So if we're given data to analyze to decide what the rate is and the reaction order, we can graph it, concentration and time, graph that information, and if we see a straight line, then we know that that is a zero order reaction. So it's pretty convenient. So this is an example of that. So we've got concentration of chemical, moles per liter, molarity over time, and we can see we get a nice straight line for that. So this means that our reaction is zero order with the rate constant equal to negative slope. So we just find the slope of the line, change its sign, and we'd have our rate constant, k. So anytime we see a graph with a straight line and we see concentration and time graphed, we know zero order reaction. Then we can take a look at first order reactions. So first order are different look a little different. The reactions that have their rate depending on the concentration of a single reactant raised to that first power, we get that first order reaction. We've looked at a number of examples of this. They've used calculus to find our new form of our rate law, which we've looked at, called the integrated rate law. We don't have to derive it as I've stated in class before, but we do know how to use it. We've done some practice at this point in calculating with our integrated rate law, but we haven't looked at the graphs of it yet. So again, here's our integrated rate law. We're used to seeing it with our natural log of A0 on this side of the reaction being subtracted, but it's been rearranged. Still all the same variables, so nothing different there. I'm going to go ahead and skip ahead. This one does, again, it's been rearranged. We've added this to the other side, the natural log of A, and that gives us again our y equals mx plus b format for this. So we can take this information, and if we graph it, we can get a straight line. Again, it will be a negative slope on our line, so we can find that slope, change it to a positive value, and we'll have our rate constant. We can also, we also have our y-intercept, which is the natural log of A at time 0. So we have the natural log of our initial concentration is our y-intercept. So if we're given data for time and concentration, and we say we graph it with 0 order, we graph the normal information, and we don't get a straight line. Well, next we can take the natural log of each of our concentration values, graph that versus time, and if we get a straight line, we have a first order reaction. So we'll take a look at it. Alright, a couple of things real quick. The units of concentration used are typically molarity, but as we've seen, we can also use pressure units. Because for gases, we have our ideal gas law, which directly relates to, or pressure is directly proportional to moles per liter. So we can use pressure units instead when we're dealing with gases. Alright, so let's take a look at these two graphs. The first graph on the left, we have concentration, well, in this case, pressure, torr. The torr, the pressure graph versus time. And then we have the same time period, so this is coming from the same data, and they've taken each of these points and taken the natural log of each point, and we've gotten a straight line. So what this tells us, we look at this first one, and this would be the data for, this is just the raw data graphed. Since that did not give us a straight line, it is not 0 order. So the raw data when graphed, if it gives a straight line, it's 0 order. But if it doesn't, we can take the natural log of it, of each point, graph it, and see if that gives us a straight line. In this case, it does. So in that case, in this scenario, because it gave us our straight line there, we can say it's a first order reaction. So we have that piece of information. And then the question at the top says, what do the y-intercepts in each of these graphs represent? So our y-intercept on our first graph tells us the pressure, our initial pressure. A little bit hard to read, but maybe you have to do a little estimating there. And then this, our other graph tells us that our y-intercept is the natural log of the initial pressure. So if I wanted to find out what that initial pressure actually was, I would have to undo the natural log, take e to the 5.0, and I got 148.4 torr, which rounds to roughly 150, which looks about where our point is over on the left side graph. So we can go between these graphs pretty easily. So if we're just given the graph on the right, and it says the natural log of pressure is graph versus time, and then straight line is produced, what's the order of the graph, or what's the order of the reaction? We could say it's a first order reaction and assume that based on the graph. So we can get some good information out of this. The other thing we could find is the slope of the line, and that can be calculated to find our k value. I have an example of that later on with another graph. The other thing we can deal with, we've got 0 order, first order, and the third one, or the next one would be our second order rate law. So we've been used to seeing our rate law written like this. To get it into the y equals mx plus b form, we're going to add this term, the a sub 0 term, to the right side to get our proper form again. All the same variables, same units, nothing crazy here. So we rearrange and get our y equals mx plus b form. So the only thing they've done is instead of taking that natural log of our concentration values, we've taken 1 and divided it by our concentration for each thing. So if this data is graphed, then we can get, and a straight line is gotten, then we know that it is a second order reaction. Now there's a slight typo in here. This natural log should not be there. I'm sorry. So ignore that. So a straight line will be created where the slope is k, because we have this positive k now, and the y-intercept is 1 over the concentration of A. So we're given a set of data for time and concentration. We graph the normal equation, the basic data, raw data. We don't get a straight line. We do the natural log of that concentration data. We don't get a straight line. The last option is to take 1 over the concentration. Where it is. I messed that up. 1 over the concentration, and if we get a straight line, then we know it's a second order reaction. Take a look. So we've got two graphs here. One of them has the natural log of our concentration, so this would be for first order. If we got a straight line here, it'd be first order, but it wasn't. So we did 1 over the concentration. We got a nice straight line. It happens to be positive slope now because of the way that the numbers work out, and that tells us this is a second order reaction. So if it was straight on the first graph, it'd be first order, but it's not, so we get second order. Again, we'd have our y-intercept here. Y-intercept is going to tell us that the initial concentration of our NO2, this is 1 over that initial concentration. So this point is at 100 molar. So if I took 100, I can calculate my concentration of NO2 from that. And we're going to take a look at how to actually calculate the slope of the line as well. So we can find the slope of the line, either any of these lines, and find our rate constant for our reaction. So we would take 2 points. I'm going to pick these two because I can. And you find the slope at those points. So it's the change in the amount in the concentration, or change in y values, over a change in time, or x values. So I picked those 2 points. So here I've got about 152 is what I estimated, minus 100. There's my y values. And then on the bottom I've got 100 seconds minus 0 seconds. Simplifies to 52 over 100, or 0.52 molarity per second. And actually that would be molarity to the negative. Let me fix these units. I'm sorry, I'm having issues with this one. This would be, because it is 1 over, there should be 1 over molarity for these. So molarity to the negative 1. So there should be molarity to the negative 1, seconds to the negative 1, or 1 over molarity times seconds. Those would be our units. To be consistent with a second order reaction, we would have to have those units to make our reaction, or our rate constant units, make sense. So that's another way we can actually use these graphs. So moral of the story here, or our overarching idea, is that we can take a set of data, we can graph the raw data, concentration versus time. If we get a straight line, we have zero order reaction, and we're good. We can find the slope, get our rate constant, and move on. If we get a curve, we go on to the next graph. We would graph the natural log of each of the concentrations versus time. If we get a straight line, we can find our slope, find our constant, move on from there. If we get a curve, then we have to try the next graph. We would graph 1 over each of the concentrations versus time. If we should get a straight line there. If you do, then you can find the slope of line and get your rate constant. So the graphs can just help us decide what the reaction order is and help us find our rate constant. You guys will be doing some practice with this in class, so it's not, so if you get confused or lost, check out the graphs, see if this helps, and you can always post your questions in the comments on the video, because I will be able to see those and try and help out.